Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 69. So in the previous lecture, we were discussing about how interstellar surface reactions can happen. We had started our module on chemical reactions in the interstellar medium, and we started off with explaining how solid phase reactions, that is surface reactions, could aid in the evolution of molecules in the interstellar medium. How was it possible? It was overall possible because the surface, right? The surface of an interstellar ice dust grain that could act as a third body, an effective third body, right? In interstellar reactions, and it could also help in the dissipation of the excess energy that is obtained as a result of a chemical bond formation. Okay, right? So this is how interstellar surface reactions could aid in how chemical reactions happen in space. Now, the example we chose was the formation of hydrogen. That is, in the last class, we saw how surface chemistry aided in interstellar reactions and how even H2 how even the simplest molecule H2, right, was formed via interstellar surface chemistry and not through routine gas-based chemistry. Okay, right? And even H2 gas was formed via, let's call surface chemistry as SC. Surface chemistry, that's it. So that is where we left. We ended last class with this at this juncture. Now in this lecture, we shall be continuing our discourse on interstellar chemistry and how especially both surface reactions and gas-phase reactions are important in the interstellar medium. Okay. Now, for example, what we shall do is we shall so in today's lecture, what we shall be seeing is how some organic molecules are also formed in the interstellar medium via surface chemistry, and also some prominent examples of gas-phase interstellar chemistry. Okay. So let's now look at how surface chemistry, right? I'm just calling it as SC in the ISM can also aid in the formation of some organic molecules in space. Organic molecules in space. Let us, for example, consider, that, let's say this is some surface, right? This is some surface, and we saw that on the surface, right? We saw that on the surface, several organic molecules can also form icy mantles, right? What is the structure of the surface? It had a core made up of some kind of an inorganic refractory material, such as, for example, silicates or titanium oxide, etc. But there always were some icy mantles of volatile organic molecules, including carbon monoxide. Okay. Now let's say that one of the carbon monoxide molecules dangles out of the ice, right? and it's just adsorbed onto the outermost layer of the surface. Let's say that, okay, right? Or the carbon monoxide alternatively would have also adsorbed onto the surface from the gas phase, because there is always a fluctuation of molecules, a flux of molecules from the gas phase to the surface and vice versa. All right. So let's say this happens, okay, and somehow carbon monoxide is here. And like we saw in the last lecture, there could always be a hydrogen, correct? So I'll write carbon monoxide this way so that the bond formation in the next step will be clearer. So let's say that hydrogen also gets adsorbed like we saw in the previous lecture, right? Please go back to lecture 68 and look at the four broad steps as to how molecules can get adsorbed and how via diffusion they can come together, etc. So by the same processes, let's say instead of two hydrogen molecules coming together, one hydrogen and one carbon and let's say in this case oxygen bearing molecule are here together, right? What can that lead to? Well, that can lead to, again, let's say this is a surface, right? And this can lead to the formation of a molecule such as this. Of course, carbon is trivalent here, but that's not a problem because this is a radical, okay, right? So I have a molecule such as HC double bond O, correct? Now, this HC double bond O, let's say that this also is in contact with some hydrogen, again adsorbed onto the surface. Now, what can this lead to? This can lead to some molecules such as something like this, right? This is just to indicate that this is adsorbed to the surface, okay? The dangling bond just indicates some kind of an adsorption to the surface, whereas a proper line indicates a proper chemical bond. All right. So now what have we done? We have accomplished. We have formed this molecule called as formaldehyde. Now go back all the way to the very first lecture in this course. Formaldehyde is a molecule that can lead to so many other products, right? Of particular interest in the origin of life, correct? So now, how did this happen? This is happening by this meaning. I'm talking about the formation of formaldehyde. It is happening via surface chemistry, where the surface provides a rich anchoring, a rich series of anchoring sites, right? It could anchor several carbon-containing species and also hydrogen. So therefore, by a series of events, as described in the previous lecture, the molecules and atom, they can come together to form organic molecules. And of course, this is of course the surface, and this can likewise, give rise to so many other organic molecules. For example, methanol. It can give rise to glycoaldehyde, which is something like CH double bond O, and so etc. etc. Okay. So the point is, just like H2 was formed via surface chemistry, the same sequence, okay, involving adsorption, desorption, diffusion, etc., etc. We have the formation of several organic molecules in space also. All right, and see, in fact, now that this is formed, as a next step, what can happen is this molecule can get desorbed, and this can be HCHO in the gas phase. That is, this is HCHO or H2CO, as the astronomers would call it. Right? So what a surface does, when I say surface, I'm talking about the surface of an interstellar dust grain. What it does is, it provides the cushion of an anchoring site so that several molecules can come together, right? Several molecules can come together and eventually form bonds. So this is how, on top of merely, primitive reactions such as the formation of H2 molecule, right? Even complicated organic molecules can form on the surface. This was just one illustration. Okay. Now, the surface also, helps in yet another way. Now, if you think about it, see, this is a very small molecule, HCHO, right? Now, if you recall from the previous lectures, probably in the first few tutorials, we were discussing about the bond energies. Now, note that the surface might be sometimes, depending on the depth of the surface, right? it may be immune to certain harmful radiations, harmful interstellar radiations, such as ultraviolet rays, or for example, some high energy X-rays or some cosmic rays, etc., etc. Okay, right? But these individual small molecules, their bonds can easily be broken. So even for example, the HH bond energy is approximately only around like 430 kilojoules, right? Now, if you bombard it with an some very high energy UV ray, right? Of course, this is going to be getting cleaved. So to avoid this scenario, the surface also helps by absorbing the harmful radiations. When I say harmful, I'm talking about high energy radiations. Okay, right? So that the molecular bonds do not get cleaved. Of course, once the molecule dissolves onto the gas phase, then it can get cleaved. But while it is still attached to the surface, right? Instead of the molecule getting impacted by the UV ray, the UV ray can just pass to the surface, and there could be minor modifications in the structure of the surface. But as far as the bond formed in the small organic molecule is concerned, that is not broken. Okay, so I'll just write it down here. Yet another way an interstellar surface. I mean, by surface, I'm talking about an interstellar grain, dust grain of dust grain aids in the formation of molecules is by bonds of small organic molecules are not cleaved by interstellar radiations. Let's say, we're talking about some kind of UV radiations, or in some cases, some cosmic rays, which is predominantly composed of protons. Okay. Right. So how does it do it? It does it by being some kind of a sink which receives the UV radiations, thereby saving the small molecules themselves. Okay, right? So when I say ensuring, how does it do it? By, I would say, how it does is it kind of takes the brunt of the radiation on itself, right? By saving the molecule. For example, if the radiation were to directly, fall on this adsorbed molecule, the bonds will break. But because the surface area is much larger, than that, corresponding to the side occupying this molecule, the likelihood of the radiation hitting the surface is higher than the small molecule. So therefore, by interacting with the radiation, right, the small molecule isn't much affected, although the surface undergoes some small changes. Okay, right? So how does it ensure that the small organic molecules bonds are not cleaved? By acting as a sink for the incoming radiation. Okay, so it does it by acting as a sink for the radiations. So what acts as a sink? It is the surface. Okay, right? The surface of the dust grain. Will the dust grain morphology and structure change? Of course, yes. But it changes, many times it changes in such a way that the formed organic molecule, its bond remains intact, and you can therefore envision the formation of more and more complicated molecules. Okay? All right. So far we were looking at what all a surface can do, right? In the context of promoting interstellar chemistry. But notice the last step in this process, for example, right? Or even for the formation of hydrogen molecule. Once H2 molecule was formed on the surface, the last step is it could always desorb. It could always desorb due to some kind of a heating mechanism. There are many mechanisms via which, the interstellar clouds can get heated, the dust grain can get heated and cooled, etc., etc. So while it gets heated, the molecule, or say for example, either the formed organic molecule or the H2 gas, right, that can desorb. So this process right here, right, this is desorption. I'll write it here. I mean, there wasn't much space, so I wrote it in small size, small font. Desorption, D-E-S-O-R-P-T-I-O-N. Okay, the atom or the molecule which is formed via surface reaction can also get desorbed. And what happens is that it is now in the gas phase. It is in the interstellar gas phase. So akin to interstellar surface chemistry, right? Interstellar gas phase chemistry is also very important, and that is what we shall be looking into in the next, in the remaining part of this lecture. And if it's not over, perhaps in the next lecture also. Okay, what we shall be seeing now is we shall be seeing about interstellar gas phase chemistry. See, how many molecules have been detected in space? Close to 300 odd, right? Now, it would be impossible for us to go through the chemistry of each and every single molecule, right? That would require its own semester of coursework, right? But instead of that, what we shall be doing is we shall look into the general mechanisms, like we saw in the case of surface, as to what are all the common gas phase processes via which chemistry occurs. Okay. Now, typically, interstellar gas phase chemistry can be classified into three types. They are, you can call them as the bond formation processes, right? Then you have what are called as the bond destruction processes. And you have yet another category called as bond rearrangement processes. Okay, so you have bond What bond am I talking about here? I'm talking about a chemical bond. In particular, I'm talking about a covalent bond. Okay, right? So that is what I'm talking about when I say bond here. All right. So these are the three common types of chemical reactions that are possible, right, in the gas phase, in the ISM, and we shall be looking into each one of them now. Let me call this like type 1, or I'll just call this BF, and this is BD, and this is, let's say, BR. So let's look at some bond formation processes. So as part of the bond formation processes, the following categories are well documented. Okay, the first one is what is called as a neutral reaction. What am I talking about? Take, for example, some molecule like a neutral reaction can be of the form methyl radical. Okay, right? This has been detected in space, and let's say your cyanide radical has also been detected. So these two coming together to form what is called as CH3CN. So this is one sort of a process. But notice that what is just like the formation of H2, wherein two radicals were formed, here also two radicals are combining to form a molecule. But what's the problem here again? Here again the problem is one of energy dissipation, right? So how will this dissipate its excess energy, right? So therefore neutral reactions, while theoretically they sound pleasing and all that, they're actually noted to be rare occurrences. Please note. Okay, so these are rare occurrences, right, due to the energy dissipation problem. All right, what is it that I'm talking about when I say energy dissipation problem? Well, the same concept that we were talking about during the formation of H2. Okay. I mean, if you're confused as to what this energy dissipation problem is, go back to the previous lecture about H2 and also go back to the key points about the differences between ISM and Earth long ago, right? Perhaps in the first few lectures in this course. So, I mean, as an example, in H2 formation. So this is a rather rare process, especially given that the number of densities in the ISM are very small. Okay, so that's why the neutral reactions are very rare occurrences. So even if the reaction is going to result in excess energy in the form of bond formation, right? Yet, because there is no other source that the excess energy could be passed on to, as a result, the neutral reactions are rare occurrences. Although there are some examples of this, okay, at higher number densities, at higher temperatures, etc., etc. So these are rare occurrences. When I say rare occurrences, I'm particularly talking about in the dense molecular clouds at low temperature. When I say low temperature, temperature less than 20 Kelvin, let's say, okay, right? So it's a rare occurrence in dense molecular clouds at let's say less than 10 Kelvin or something, less than 10 or 20 Kelvin. All right, but those are the physical conditions in the dense molecular clouds, right? Okay. Now, one way via which this reaction could happen is could occur. Okay, is what is called as radiative association. So I'll just call this I'll call this A1. So this is going to be A2, which is a special, I would call this, okay, but a special way to facilitate neutral reactions. That we discussed in point A1. So this special way is going to be via what is called as radiative association. Now, what is radiative association? Let's say you think of some species like X plus Y giving XY. Now, what's the problem with its formation? The problem with its formation is the dissipation of the excess energy, assuming some energy is released. Okay, if energy is actually needed to produce this, it may not even occur. Okay, I will come back to this in greater detail when I talk about the thermodynamic aspects of interstellar reactions. But for now, we have this condition where the excess energy is difficult to get dissipated. Okay, such that XY still stays intact. But let's say that this liberates a photon. Okay, this liberates a photon. This HU is just to indicate that I'm as a consequence of this result, this molecule XY is liberating or radiating some photon. Okay, this process is what is called as radiative association. In other words, the association of X and Y results in the generation of some radiation in the form of a photon. Okay, so this radiative association could facilitate the neutral reactions. All right, so but there is still a drawback. Okay, the drawback is still that whereas see, for radiation to typically when a radiation to happen, right, what do you need? You need the molecule to get excited and then come back, right? What are the common causes of excitation? Well, due to thermal excitation, if the temperature keeps increasing, the vibrational levels in these molecules get more and more activated, right? The higher modes are activated, or you need a higher number density. Okay, so even though radiative association is one way to facilitate the neutral reaction, note that radiative association, I'll just call this RA. RA is also challenging. Okay, is also challenging. I mean, at very low temperature and with the number densities being very low. And with low number density, because you don't have a sufficient mechanism for the radiation to actually occur. Yet, it has been proposed as one feasible way via which the neutral-neutral reactions can also occur in the ISM. In fact, I'll also add one more point in this context, that it in fact is very difficult. It is very difficult to, to even model radiative association in a laboratory on Earth, because see, if you want to mimic interstellar conditions truly, the temperatures have to be low. But let's assume that somehow modern cryogenic technology is good enough that you can cool things down to very low temperature. But even then, this to mimic the low number density of the ISM is a huge challenge. So therefore, while radiative association is a lucrative proposition to facilitate neutral-neutral reactions in the ISM, it still is somewhat difficult to do this. Okay, so please note this. Okay, so as part of the bond formation process, the first one we saw was a neutral-neutral reaction. The next example is what is going to be called as a grain surface formation. Point B, grain surface formation. Now, an example of this type, a generic example of this type, is going to be something like X, let's say, in the gas phase, plus Y, XY in the gas phase, plus the surface. Now, this is of the form AB, A plus B, I mean, the product of the form A plus B. There is not just one entity here, right? So what is the advantage we get? The energy dissipation problem is already taken care of, and the surface acts as an effective third body. What is an example we just saw, right? An example could be, say, something like carbon monoxide in the gas phase, or say something like HCO in the gas phase, plus some H attached to a surface, giving something like, or H2CO. I'll write it the way astronomers write it, right? In the gas phase, plus a surface. So this is an example of the grain surface formation. So I think it's time for this lecture. So in this lecture, I gave you an idea about how organic molecules could be formed via interstellar surface chemistry also. And I introduced you to the idea of interstellar gas-phase chemistry, which could be broadly classified into three types of chemical reactions: those involving bond formation, those involving bond destruction, and those involving bond rearrangement. As part of the bond formation processes, we started off by studying about the neutral-neutral reactions and how radiative association, which is still challenging, could facilitate the neutral-neutral reactions. Then I gave you the example of a grain surface formation, and with that, I end this lecture. We shall continue from precisely this point in the next lecture. Thank you so much. Have a good day.